We've introduced conditional proofs, but we need another kind of subproof, what are called indirect proofs, sometimes known as reductio ad absurdum proofs. And the idea is discussed in the text is that sometimes the way to prove that something is true is to show that if it's not, you're led to an absurdity. In other words, if I want to prove x, sometimes the thing to do is to assume not x, show that that leads to an absurd result, and then conclude x must be true after all. Likewise, if I want to prove not x, I can show that x leads to an absurd result. So what we're going to do here is work through a few examples of this to see what the system actually looks like in practice, what it looks like given our way of setting up proofs. And we'll start with this proof here. So our premise is if not p, then p. And the conclusion is that p. Now that may seem a little odd, but if you were to check with the truth table, you'd see that it's correct. What we want to do is see how to prove it. So here's our premise. We've got that. Here's our goal. And so what we're going to do is we're going to prove p by assuming, as we might say, its opposite. We're going to assume not p. That's an assumption. And what we write is an assumption for contradiction. We're looking for an explicit contradiction. What we mean by an explicit contradiction is a sentence x, a sentence not x, put together with an and. When we get to that, we've got our contradiction. And now you can see we're going to get there very quickly. And this is really a good way of seeing why this actually does imply this. Suppose p isn't true. Well then, by modus ponens, we get p. Which would mean that we'd have both not p and p, and that is a contradiction. Contradictions can't be true. So what we can do here is we can write p and not p. That comes from 2 and 3 by conjunction. And in an indirect proof, since your goal is to derive a contradiction, we've done it here. We've gotten a contradiction. Assuming not p led us to an absurd result. And so the conclusion we have to draw, let's put in our scope line here, is p. And that's an example of an indirect proof. The justification for p is going to be 2 through 4 indirect derivation. ID for indirect derivation. So the idea again was the claim was that this premise implies this conclusion. We show it by assuming the opposite, the denial of this conclusion. And we show that once we've assumed that, we're led to a contradiction. When we get the contradiction, we can discharge our assumption, put in our scope line, and here what we did is we assumed not p, we dropped the tilde and got p. That was our goal. If our goal had been not p, we could have gotten that too, but for the time being we'll stick with this. In an indirect proof, if you've assumed something that has a tilde, you can drop the tilde at the end or add a tilde. If you've assumed something that doesn't have a tilde, that occasionally comes up, then you add the tilde at the end. So this is an example of an indirect proof. Let's go on and try another. Let me just rearrange this so that it's fit to work on. Okay, here's what we're going to do. We're going to start with a premise. Our premise is going to be not p and not q. That's a premise. The conclusion that we want is not p or q. Okay, so how are we going to do this? Well, we're going to do it indirectly. On line 2, we could go ahead and do some simplification here, and that would be okay. But when you're beginning to do this style of proof, it's probably a good idea to get into the flow of the thing first. And so what we're going to do first is just assume the opposite of what we want to prove. We want to prove not p or Q. So in this case, we're going to assume P or Q. That's an assumption for contradiction. And we're going to show that this leads to an absurdity. This leads to a contradiction. Now we can go ahead and do the simplification steps. We could have done them before, but we'll do them now. So one simplification gets us not P. We'll go ahead and do the next simplification here, though we could do it in a different order if we liked. We have, once again, one simplification gets us not Q. And now we can go ahead and use our rule of disjunctive syllogism. So it really doesn't matter which way we do it. We'll get rid of the P here. We'll use 2 and 3 disjunctive syllogism and get Q. So 2, 3 disjunctive syllogism gets us Q. And now you notice we have not Q on one line, we have Q on another line. To complete the proof, we put things together into an explicit contradiction. Q and not Q. That's by 4 and 5 conjunction. And that completes the proof. That is to say, we need to add one more line. Our subproof is complete. We got to a contradiction. That was our goal when we began the subproof. We've gotten there. So we cordon this stuff off. We put in our scope line. And what we can conclude is what we originally set out to conclude. Not bracket P or Q. So again, we assumed the denial of what we wanted to prove, but in this case we did it by dropping a tilde. And then at the end we said, well, dropping the tilde led us to a contradiction. We will now conclude that when we add the tilde back on, we get what really follows. And this makes sense, because this, after all, is one way of saying neither P nor Q, and this is another way of saying neither P nor Q, so it should turn out that we can make this proof go through. And in fact, it does. The justification here is 2 through 7 indirect derivation. Now, just as a sort of a shorthand, it can get really tiresome to write these contradictions out explicitly. So what we're going to do is, instead of writing out the contradiction explicitly, we're going to use this symbol here, this perpendicularity sign. We just call it perp. And when you have two lines that contradict one another, and they're both available, you can then write the perp symbol as a way of indicating that you got your contradiction. So what we've got here is the perp symbol justified by 4 and 5 because they contradict, and now our proof is complete. Okay, let's look at another example here that is particularly simple, and so simple in fact that it's sort of silly to go through it, but we will nonetheless. Here's a theorem. Not, whoops, pardon me. The theorem is not P and not P. Well, that better be a theorem because it says that contradictions aren't true. How do we prove it? We're going to prove it indirectly. We want to prove not P and not P. We assume P and not P. Assumption for contradiction. Well, guess what? We don't have to go searching for our contradiction. In this case, we actually have it in one line. And so we can conclude not P and not P. Put in a scope line here. And this actually is a legitimate proof. 1. Indirect derivation. It's a trivial example of a proof, but it's an example of a proof. Now here we couldn't use the perp sign because we had to make clear what the contradiction, that we actually had something that amounted to a contradiction. You don't use the perp sign to indicate an assumption, but I think you get the idea. Okay, so one more. This next one is a bit more challenging. This seems like it should be a theorem. And it is. P or not P. That ought to be a theorem. I mean, that seems like a pretty trivial thing, logically speaking. And it is a theorem. So let's see how we'd prove it. Well, this is where things get sort of interesting. We need to make an assumption. It certainly doesn't make any sense to try to do an assumption for conditional proof. We're not trying to prove a conditional. So we assume the denial of what we want to prove. Assumption for contradiction. But now the problem is, what in the world do we do next? Well, I want you to maybe pause and think about this after I make the remarks that I'm going to make here. But here's the idea. We need to get a contradiction. We need to get an explicit contradiction. But if the proof works, then implicitly we already have one. We know that implicitly this is contradictory. We know that this can't possibly be true. And so it wouldn't be surprising if from this contradiction, this implicit contradiction, we could actually derive anything at all. Now, what would be useful to derive? What would help us actually complete the proof? Well, suppose that we could actually prove P or not P. Now, you might say, oh, hold on, that's what we'd set out to do. Well, yes, that's right, but we're in a different context here. We've now got an assumption that we can use in the proof. And so we're saying, relative to this assumption, can we prove P or not P? If we can, we could put that proof of P or not P together with the assumption, and we'd have a contradiction. So how might we do this? Well, suppose we had P. If we had P, then we could get P or not P. So the clue here is this. If we had P, we could finish our indirect proof. It looks a little funny, it's a little bit awkward, but it would work. How might we get P? Try an indirect proof. Try to prove P indirectly and see where you get. This is going to look a little bit funny when it all works out, but pause, give it a try, and then start back up again. Okay, here we go. We want to prove P for strategic reasons. We make an assumption for contradiction, so now we've got an indirect proof within an indirect proof. Well, okay, we've got not P, which means we can get P or P. This is going to be a little bit squirrely, but bear with me. I can get P or not P from 2 by addition. Now notice, I've got a contradiction. Line 1 contradicts line 3. So on line 4, I can write the perp symbol, and I can justify it by referring to lines 1 and 3, and that completes this inner indirect proof. That means that we have now proved, relative to our assumption, that we get P. Okay? So this comes from 2 through 4 by indirect derivation. Now, what next? Well, remember why we wanted to get P in the first place. It's because that would let us get P or not P. Now you might say, well, we already got P or not P. Yes, we did, but it's now behind a scope line. We only proved this on the assumption of not P, and that assumption is now gone. It's now been discharged. So we can't pull this P or not P out of here. We've got to go ahead and do it again. Annoying? Yeah, but that's how it works. So here we go around the mulberry bush. P or not P on an available line now from 5 by addition. And then notice line 1 and line 6 contradict one another. So we can write our perp symbol. The justification for it is line 1 and 6. And that means that we've gotten the contradiction that we were originally looking for. So we'll put in our scope line here. And that means that on line 8 we can conclude P or not P, assuming its denial led to a contradiction. So 1 through 7, indirect derivation gives us P or not P. Now you may very well want to go over this again. This takes a little bit of getting used to. But indirect derivation is a really important part of our proof system, and so I wanted to get you started on it. So have a think about all this, play it again as you need, and then you can do the other exercises in the book, which, by the way, have solutions.